Hello, this is Math Jazz from Almost Cool. This is I guess the sixth live stream in this series, and I look forward to answering all of your questions about calculus. Today I have some questions prepared. Let me clear the screen. So, that didn't quite get all of them. Anyway, so today I have a list of questions to solve. The first of which is going to be going to find the critical points of x to the fifth here we go. X to the fifth divided by 5 minus x to the third divided by 3. There we go. So, to find critical points, we have to have the derivative of our function equal to 0. And so we're going to use the power rule on this. We have our f of x equals, well, we take the power 5 and multiply it by the term. So that gives us x with the denominator will cancel with that coefficient of 5. And then we subtract 1 from the power, leaving x to the fourth. The power rule on the second term gives us x squared, same way that the derivative of the first term gave us x to the fourth. And now we have to worry about where does this derivative equal 0? So we have to factor it. So we have f prime of x is equal to x squared times x squared minus 1. So we could see that the only way for the derivative to be 0 is if the x squared term is 0, or if the x squared minus 1 term is 0. So that gives us that x is either 0, 1, or negative 1. Math form doesn't like commas. Here we go. X equals negative 1, x equals 0, and x equals 1. So those are our critical points of the function, places where the derivative equals 0. So the next thing we might want to know is how do we test which of these are local maxima or minima? So we will take the second derivative test to figure that out. So we have our derivative here is x to the fourth minus x to the second. So our second derivative should be easy to find. I'll put it right here. We just use the power rule on each of the terms. So we're going to get f double prime of x is equal to 4x cubed minus 2x to the first. Now the second derivative test says that the sign of the second derivative at a critical point determines whether the critical point is a maximum or a minimum. So we plug in negative 1, and we're going to get negative 1 cubed is negative 1 times 4. So we have negative 4. And then negative 2 times negative 1 is positive 2. So we have negative 4 plus 2 is going to be negative 2. So we know that f double prime of x, f double prime of negative 1 is negative. The second derivative being negative at a critical point tells us that that critical point is a maximum of the function. So we have a local maximum at x equals negative 1. Now, one thing that we do know about this function, since its powers are all odd and this is a polynomial, we know this function is an odd function. So that means it has rotational symmetry about the origin. And so that means that our local maximum at negative 1, when we rotate 1/2 turn around the origin, becomes a local local minimum at x equals positive 1. But we can use the second derivative test to figure that out for us as well. So let's plug positive 1 into our derivative. So if we plug positive 1 into the second derivative, this derivative here, we get 4 times 1 is 4, minus 2 times 1. So 4 minus 2 is 2. So that tells us that our second derivative at the point x equals 1 is positive, and that tells us we have a local minimum at x equals 1, which is what we knew because of the symmetry of the function. So we can now test we can use the second derivative test to test the point x equals 0. We plug 0 into this function and we get 4 times 0 minus 2 times 0. But that is 0. And the second derivative test fails when the second derivative is 0. It tells us no information. We don't know if we have a maximum or a minimum there. So failing at the second derivative test forces us to use the first derivative test. So we go back to our first derivative, which is here. Actually, factored form is our better bet. So we know that since this derivative factors so that its roots are at negative 1, 1, and 0, those are the only three places where this derivative can change signs. And what we care about is what is the sign of the derivative a little bit bigger than 0 and a little bit smaller than 0. And by a little bit, I mean close enough to 0 that we don't have a root between where we're checking and 0. So we pick any number between 0 and 1, we'll be fine because the only roots are negative 1, 0, 1. Picking a point like a half, there's no root between 0 and a half, so it accurately tells us the sign to the right side of 0. So we're going to plug in a half and negative a half into the first derivative. That'll tell us the sign of the derivative between negative 1 and 0, and the sign of the derivative between 0 and 1. And that'll tell us whether this function is increasing or decreasing. Sorry, that'll tell us whether the function has a maximum or a minimum at 0. Or maybe it has neither at 0. So anyway, I'm going to take this derivative and I'm going to plug 1/2 into it. 1 half, half, and 1 half. This is negative. So that means that to the right of 0, our derivative is negative. And we're going to do the same thing, plugging in negative a half. And that'll tell us what the sign of the derivative is on the left side of 0. So f of negative 1 half equals negative 1 half squared times negative 1 half minus 1. We see that's also a negative number. So, since the sign did not change, we know that even though we have a critical point at 0, that critical point is not a maximum or a minimum because the sign of the derivative did not change. Our function was decreasing before it hit 0, and it was decreasing after it hit 0. And so there's no maximum or minimum there. So there we go. Okay, so that is the first problem that we're going to be working through. We found the critical points, and we checked which of those were extrema. And now we'll clear these off the page. Okay. Our next question. We're going to evaluate a limit. Our limit is the limit as x goes to 0, which I am not sure how to write. X squared secant of x divided by tangent of x minus sine of x. There we go. So we're going to take the limit of this expression as x goes to 0. So normally, well, sometimes it's the case that doing a little bit of simplification makes the problem a lot easier to do. If we were to plug 0 in right now, we would get a 0 on the top because we have 0 squared times 1. And then we'd divide by 0 minus 0. So this expression here is 0 over 0. It's indeterminate, so we can use L'Hopital's rule. But secant and tangent and sine, these derivatives may be difficult. So I'm going to say, first let's pull this secant into the denominator of the expression. So we'll do that. Secant in the numerator is the same as cosine in the denominator. So we get cosine times tangent, leaves us with sine. And then we get cosine of x times sine of x, like so. And you're saying, that doesn't look easier. Well, give it a moment. We'll see. So what we can do now is we can split this fraction into two fractions being multiplied by each other, or one by the other. So the first one, let's have be x over sine of x. So we factored an x out of the top, and we factored a sine out of the bottom. What are we left with now? Oh, it automatically simplifies for us. That is fantastic. That's not what I want at all. So let's do that in two different lines. Okay. Hopefully this isn't too hard to read. There we go. So the top expression is what I got from moving the secant to the denominator. And this expression is what I got when I factored an x out of the top and a sine out of the bottom. So I get x divided by sine, or x times cosecant is what it's forcing me to place it as. And then I'm left with an x on top and a 1 minus cosine in the bottom here. So I have this fraction is equal to this fraction times this fraction. But we know that the limit as x goes to 0 of x over sine x is 1. So this limit here goes to 1, and we don't know what this limit goes to, but we can use L'Hopital's rule on this. And this is simpler than what we started with. So we use L'Hopital's rule on this fraction, and we're going to get 1 as the derivative of the numerator. And we get sine in the denominator. So L'Hopital's rule says that the limit of a fraction that is an indeterminate form is equal to the limit of the derivative of the numerator divided by the limit of the derivative of the denominator. So the derivative of the numerator is 1. The derivative of the denominator is going to be, well, the derivative of 1 is 0. Derivative of cosine is negative sine. And the negative cancels with this negative here, leaving sine. So we get the limit as x goes to 0 of cosecant and that limit doesn't exist. So this limit doesn't exist. This limit, it is 1, so that means that the limit as a whole didn't exist. Or we could do L'Hopital's rule on this function directly. We'd have to use a product rule on the top, and we'd have 2x secant plus x squared secant x tangent x. It would be kind of bad. In the end, we find out that this this limit doesn't exist. Okay, so let's do another one. Let's see. Let's do an integral. Or let's at least approximate an integral. So we'll approximate the integral of x cubed on the interval -1 to 2. Using right endpoints and 3 boxes, or 3 rectangles. So this is a Riemann sum. And it shouldn't be such a bad one. So the Riemann sum is going to be the sum of the areas of the 3 rectangles. The 3 rectangles are going to have their height given by the value of the function on the right corner of the rectangle. And the width of the rectangle is going to be, well, I didn't specify that, but we want to have equal width rectangles. There we go. So we'll rewrite the question like that. So the first rectangle starts at -1 and ends at 0. So the width of this rectangle is 1, and the height of the rectangle is 0. So we get width of 1, height of 0, plus the next rectangle starts at 0 and ends at 1, and its height is going to be f of 1, so 1 cubed is 1. So we have a width of 1 plus a height of 1. Sorry, times a height of 1. So our first rectangle had no height and a width of 1. Our next rectangle had a height of 2 and a width of 1. And our last rectangle has a width, well, the width is still going to be 1. It starts with its left bottom corner at 1, and it ends with its right bottom corner at 2. So that means that the height of the rectangle is going to be f of 2, and f of 2 is going to be 2 cubed, which is 8. So our rectangles are going to have width 1, and then height 0, 1, and 8 respectively, and the Riemann sum is just the sum of these rectangles. So the approximation that we got is 9. We have 9 units of area in our rectangles. Now, let's say that this question were asked and we were asked to do left endpoints instead. Well, it works the same way. Ooh. There we go. So now the width of our rectangles are still going to be 1 because we have 3 equal width rectangles. But the heights are going to change. Now, instead of using the right endpoint of each rectangle, we're going to use the left endpoint of the bottom of each rectangle. So the first rectangle is going to have a height of -1 cubed, which is -1. Remember, going down counts as negative height for us. So the height of the first rectangle is -1. The first rectangle goes from -1 to 0. The second rectangle goes from 0 to 1. We plug 0 in to find the height of the second rectangle. So 0 cubed is 0. We multiply that by our width. We get 1 times 0 is the area of the middle rectangle. And the third rectangle goes from 1 to 2. So the left endpoint is at 1. 1 cubed is 1, and that becomes the height of this rectangle. And so now, the sum of these 3 areas of these 3 rectangles is our Riemann sum. The negative area on the left side cancels out with the positive area on the right side, and we get an integral of 0. Now, if we had more boxes, we would get a better approximation of the area under the curve. But 3 boxes is not a very fine partition. It's a very, very coarse estimate. And that's why 0 and 9 seem so far apart for such a narrow region from -1 to 2. But doing more boxes, doing more rectangles is not really any harder than doing 3. We just have to count up more boxes. And the process is pretty much the same. You still figure out the height of each box, the width of each box, multiply them together, and add all of the areas at the end. Okay. But speaking about Riemann sums reminds me of sigma notation. So let us look at a sigma notation problem. We'll have to delete all of this. There we go. So this one is, we're going to evaluate the expression, and our expression will be from I equals 1 to 9 to 5. Oops. There we go. Of 2 times I plus 5. There we go. Ooh, that looked awful. There we go. Okay, so we want to sum this expression over the range 1 to 5. For all of you that are computer science majors or have any experience programming, this is a for loop. Yeah, so we have our iterate, our local variable, being initialized at 1. We're going to perform the operation of addition, adding each of these terms and iterating every time. We add 1 to the local variable every time until we hit 5, and we stop on 5. So I guess that is a difference between this notation and a for loop, is that usually you stop the for loop before it performs the last computation. So you do for I equals 0 to I less than 5, and so it'll stop on 4. For this notation, we're going to stop on 5. 5 will be the last time that we execute the code, or we execute the step in the algorithm. So this expression here becomes, well, we plug 1 into this, so we get 2 times 1 plus 5. And that's our first term in our sum. And then we increment, we get 2 times 2 plus 5. I'll put some extra parentheses to make things more clear what we're doing. So notice that I've taken this expression right here, 2i plus 5. I plug 1 into that, and that became this term. Now, after I plugged 1 into that expression, I plugged 2 into that expression, and that became this term. And I'm going to go all the way up until I plug 5 into this expression. So I get plus 2 times 3 plus 5 plus 2 times 4 plus 5 plus 2 times 5 plus 5. And I multiply that all out and add that all up, and I get 55 as the value for this expression. So that isn't a lot of work when the starting number and the stopping number are close together. But what if I had asked for the sum from I equals 1 to 25? Now, a computer can go really fast, and it actually can compute all those really fast. But if I needed to do this by hand, how would I do this? Well, there are a few formulas that we get to memorize for doing calculus, for doing Riemann sums. And I will give them to you here. Here's the first one. So the sum from I equals 1 to n of I is equal to n times n plus 1 divided by 2. I wonder if math form can handle this. Oh, do we need an extra equals there? Oh. Has no closing bracket. Well, that's bizarre. I see a closing bracket right here. Or maybe, there we go. There we go. So our sum of I is a half of n times n plus 1. We have two more formulas that we will memorize. We get an I squared formula and an I cubed formula. This one is like so. So our formulas are the sum of I squared from I equals 1 to n is 1/6 n times n plus 1 times 2n plus 1. This, I think, is the hard one to memorize. The sum of I cubed is 1/4 n squared times n plus 1 squared. Now, this expression here has i's and constants in it. So if I'm going to rewrite this expression using these formulas, I can rewrite it like so. So I have 2 times I. So that's 2 times my formula for I. Notice that the 2 in the denominator and the 2 in the numerator will cancel. And then I'm going to add the distance between 1 and 25. There are 25 numbers being counted. 1, 2, 3, up to 25. So I will multiply our constant by 25 and get 125 as our new constant. And this right side of the equation has no sigmas anymore. Also, I know the sum stops on n, this sum stops on 25, so I can replace the n's in the equation with 25. And that gives me 775 as the answer. Yeah, 775 is the answer once we change the expression to go from 1 to 25 instead of 1 to 5. If I'd plugged 5's in for n here and here, I get 5 times 5 is 25 here. Then I end up with 55, like the original question said. But the longer sum with extra terms is the motivation we have for developing these formulas that allow us to simplify long sums, sums with lots of terms in them. So let's do another one of these. Let's see. So if we were doing the sum of 1 to 100 of I. Now, I could, if I were patient, I could write 1 plus 2 plus 3 plus 4 plus 5, and so on. That would be exactly what this expression means. The sum from 1 to 100 of I. You know, of course, I'd have to actually stop at 100. But using our formula that we had from earlier, we can rewrite this as n, which is 100, times n plus 1, which is 101, divided by 2. 100 divided by 2 is 50. 50 times 101 is 5,050. And so that is a lot faster than adding 1 plus 2 plus 3 plus 4 all the way up to 100. This problem here was solved by Gauss when he was a young child. I think he was only 10 years old when he solved this for his teacher. And he would have been, I guess, the first person to realize the formula n times n plus 1 over 2. Okay, so let's do another problem. Let's see. How about using Newton's method to find a root of f of x equals sine of x plus x with x0 equal to pi over 2. What is the value of x sub 1? Wow. I guess text form can't handle math symbols. Okay, so that almost fixed this so that it almost is readable. Oh, it looks like Kyling is watching us. Hi, Kyling. Okay, so using Newton's method to find a root of this function, with that as our initial guess, what is the value of our first approximation? So the formula for Newton's method looks like this. The nth approximation is equal to the n minus 1th approximation, or n minus first. That'd be x sub n minus 1 minus the function's value at x sub 1, or n minus 1, divided by the derivative's value at that same point. Okay, so here's the equation. So if we have an approximation, we can find the next approximation, which should be better, by taking our first approximation and subtracting the function's value at that point divided by the derivative of the function at that point. Okay, so with that information, we have to just find the derivative of this function. So that's not so bad. The derivative of sine is cosine, and the derivative of x is 1. So here's our derivative. Now we have to plug in pi over 2 into the function. So here's our function, here's our derivative, and then we plug all of those values into our formula. So let us do that. Oops. Okay, so we plug in pi over 2 and that's going to be our derivatives value, and we will plug it into our function as well. So that's going to be sine of pi over 2 plus pi over 2. So our original function was x plus sine x. And we get 1 and 1 plus pi over 2. So plugging all of these into the formula gives us that x sub 1 is equal to x sub 0. So x sub 0 is pi over 2 minus our function's value is 1 plus pi over 2, and our derivative's value is 1. So that gives us x sub 1 is negative 1. And that's our first approximation. It should be slightly better than the one that we had. And then if we continued plugging negative 1 into these functions and those values into our formula, we'd get x sub 2, which should be a better approximation than the one that we had. Okay, so let's do another problem. Let's talk about antiderivatives now. We've talked about some derivatives and we've done some Riemann sums, but we haven't done any antiderivatives today, I don't think. So, how about what is the antiderivative of the following function? And that function will be, let's see, I have 1 over f of x is equal to 1 over the square root of 1 minus x squared. So, this function, if we think hard about it, we can remember that this is the derivative of arc sine. So this might be cheating, but if we know that arc sine's derivative is this, then the general antiderivative is going to be arc sine plus some constant. So capital F is equal to arc sine of x plus c. Now, you might be thinking that's unsatisfactory. But what we can do, if we wanted to find an antiderivative, is we could do something called a trig substitution. So looking at this expression here, this fraction, we want to take advantage of the Pythagorean theorem. So looking at this here, I can see that 1 minus x squared square root, we want this to be we want to let x equal sine of y, because then we get 1 minus sine squared y, and we can use the Pythagorean identity to convert that into cosine squared and kill off this square root. So first, let x equal sine of y. Then f of y, or f in terms of y, we get f of x there we go. F of x is equal to we have sine of x squared. Like so. That since cosine of squared plus sine squared is 1, if we subtracted sine from both sides, we'd get cosine squared equals 1 minus sine squared. So this becomes the square root of cosine x squared. And the square root of cosine x squared becomes just 1 over cosine. But here's the problem. Well, I'm sorry, these should all be in y's, not x's. Here we go. Y squared there we go. Y's. There we go. So now we have f of x is equal to secant of y. But since we were integrating with respect to x at first, we can't just take this integral of secant of y. So this expression here, written as an integral, is going to be dx over the square root of 1 minus x squared, and then we integrate that to get the antiderivative. So this expression here is dx. We're taking the antiderivative with respect to x, but when we're converting into these y's, we have to convert everything into these y's. So all the way down, dx, dx. What we want, and that's weird. Okay. We'll just have to deal with the dx being in the front there. Anyway, we can't integrate an expression of y's with respect to x without converting our dx into some expression of dy. And the way to do that is we have to go back to our substitution, which is here. We'll take the derivative of both sides. Derivative of sine is cosine. Derivative of x is dx. Derivative of y is dy. And that gives us this expression here. So now we plug dy cosine y in for dx. And that'll complete the transformation from an integral problem about x's to an integral problem about y's. So we get dy cosine of y. But then the cosine in the numerator will cancel with the cosine in the denominator. And we just get f of x equals dy. And the integral of 1 dy with respect to y is y. So we get that capital f of x, that is the antiderivative of x, is just equal to y. But y is equal to, well, if sine at y equals x, then y equals arc sine of x. Plus a constant. Oh, there we go. So the antiderivative of 1 over the square root of 1 minus x squared is arc sine of x plus a constant, which is exactly what we said it would be when we said, oh, we're just going to use our memorized derivative backwards, which is what we want. We don't want to get different answers via different methods. If we get different answers going different directions, different methods, that means one of our methods must have been wrong. Either that or the two things we think are different are really the same. But so first we took the antiderivative by just remembering, oh look, it's the derivative of something that we already know. And then we did this trigonometric substitution to convert the problem from an antiderivative of a function of x into an antiderivative of a function of y, and then converted the y back into x to find the antiderivative as a function of x. So I think that that's the first integration technique that I've done in a live stream, other than just like the power rule for integrals. Okay, let's do one more integral, and then we will wrap up the live stream. So, evaluate the integral, and our integral will be, how about, I'll have to figure out how to do an integral symbol in Mathematica. Let's do the square root of 16 minus x squared plus, how about, x plus 4. So we're going to integrate this function on the interval from 0 to 2. Sorry, 0 to 4. There we go. So this function will be our integrand. We'll integrate it from 0 to 4. But we're going to cheat. We're going to use geometry to do it. At least we're going to use geometry to take this part. That is the equation of a circle of radius 4 centered on the origin. Which means that this integral of our function f can be split into 3 integrals. One integral here, one integral here, one integral here, and this integral is just the area of 1/4 of a radius 4 circle. So let's do that. So we have the radius is 4 and the area is pi r squared. So pi times 4 squared divided by 4, because we're only looking at the upper right quadrant of the circle. Okay, so that'll be the area of this chunk of the graph. And now we're left with the area under this line between 0 and 4. Now, we could use a trapezoid to do that, or we could do a triangle for that part and a rectangle for that part, but I think that it's actually just as easy to do an integral on this part. So the way that we're doing the integral on this whole function is we're splitting it into 2 integrals, one on our polynomial part, x plus 4, one on our circle part. The circle part we will evaluate using geometry, and the polynomial part we'll evaluate using regular calculus. So math form, the antiderivative of x is x squared over 2. The antiderivative of 4 is 4x. So the area is going to be this expression x squared over 2 plus 4x with 4 plugged into it, minus this expression with 0 plugged into it. So let's do that. Here's times 0 and 0. This will be times 4 and 4 squared. So the area under this curve is 24. And the sum of these two areas is the area under the curve f. So the integral of f on the interval 0 to 4 is going to be 24 plus 4 pi. Well, thanks for watching the live stream today. I hope that we were able to address meaningful and and important questions in calculus today, or at least give you some practice in doing some calculus problems today. Thanks for watching. I hope you have a great day. See you next week. Goodbye.